All right, these are the uniform circular motion notes. There are a lot of notes within this section, but we will be breaking it up into chunks. So this is just the uniform circular motion part. All right, so circular motion equations. First of all, we've already talked about frequency. Frequency is the inverse of period, or how many happen in a certain amount of time. So when we're talking about circular motion, frequency is how many circles happen in a certain amount of time. So it is the inverse of period, though, and it's on your formula chart of 1 over t. Now, we also have an equation for the speed. This would be the circular motion speed, or the tangential speed is how we talk about it. And tangential speed, normally we've talked about speed or velocity as displacement divided by time. Well, the displacement of a circle is its circumference. So we use the 2 pi r, because that's the formula for the circumference, and the time for a circle is the period. So we would say 2 pi r divided by t. This formula is not on the formula chart because it really is just d divided by t. Okay, so just remember that for circles it really is just d divided by t, just the d is the circumference and the t is the period. Now we could also rewrite this formula. Instead of dividing it by time, we could multiply it by frequency, since frequency and period are inverses of each other. So 2 pi rf is also another way of looking at this formula. Okay, so again, these are equations. You should have a spot in your notes to be writing these down. Okay. So example 1, normally I don't do examples on these notes, but since I'm not here, these are kind of taking the place of that. So I have a kilogram body, 2 kilogram body object that's tied to the end of a cord and whirled in a horizontal circle that has a radius of 2 meters. If the body makes 3 complete revolutions every second, determine its period and linear speed. Linear speed is the same as its velocity, or tangential speed. Okay, so if it makes 3 revolutions every second, revolutions per second is a frequency. So, we also were given its mass, and we were given the radius. So we know the mass, the radius, and the frequency. So to find the period, we just need to take the inverse of the frequency. So we would do 1 divided by the frequency, which would give us 0.33 seconds. So that's something we did in the last unit, so that should be very doable. Then to find the linear speed, we could do 2 pi r divided by, and that really should be a capital T, but it's the same concept of the period. So we could do 2 pi r, or we could do 2 pi rf. We could get the same answer. So we could do 2 times pi times 2 meters divided by 0.33 seconds, unrounded and brought down, which would give us 37.8 meters per second. Like I said, though, we could just also do 2 pi times 2 meters times 3 revolutions per second. And then those revolutions just really wouldn't be a part of our answer because it's just the number that's per second. Okay, so do you guys remember these? They've been something that you played on. So these merry-go-rounds, actually, we can talk a lot about circular motion. And if you think about it, the person on the outside has to travel this further distance in the same amount of time. So the person on the outside is always going a faster speed than the person on the inside. So when we're talking about uniform circular motion, this is the motion along a circular path where there's no change in speed, just a change in direction. Okay, so the velocity is actually constant all the way around, and it's considered to be tangent to the circular path if it goes flying off. There is always a force, and that force is constant, and it's always towards the center. We'll talk about that in a little bit, but that's known as the centripetal force, and that's holding it in the circle. All right. So is there an outward force on the ball itself? That is a good question. Okay. So the question of the outward force can be resolved by asking what happens if the string actually breaks. Okay, if the string actually breaks, then it does just continue off in a straight line path that's tangent to the circular path, which would mean that there is no outward force as it might be expected. So the ball just moves tangent to the path, but not outwards. Since it doesn't move outwards, there's no outward force. So when the force is, oh, please don't do that. Okay, we're not going to move that. When the central force is removed, the ball just continues in a straight line path. So since that central force or centripetal force is taken out, since it just keeps going in that straight line path, that would mean there's no other forces acting on it. So centripetal force is needed to change the direction and keep it moving in a circle. That force is always directed towards the center. Okay. Now, centripetal acceleration, because there's a force, there must be an acceleration. Now, really, an object that's experiencing uniform circular motion is always accelerating because its velocity is changing directions. Not because the velocity value is changing, but the direction is changing. So notice that these vectors v1 and v2 are the same size, but they're in different directions. Because it's changing directions, it is accelerating. Because it's accelerating, because there is a force being applied to a mass. Now, to calculate centripetal acceleration, we'll use the linear velocity and the radius of the circle. So this formula is on your formula chart. It is listed as AC for centripetal acceleration, and it's v squared divided by r. This v is that tangential or linear velocity divided by the radius. Okay. Notice that the centripetal acceleration is always facing towards the center because the acceleration and the force are always in the same direction. Okay. We could also substitute the formula that we've learned for v, which was our 2 pi r over t, or 2 pi rf. And if we do that, then we get a formula of, oh, and I really need to be able to show you that. It is 4 pi squared r divided by, and this could be a capital T for period squared, or it could have been that AC equals 4 pi squared r multiplied by f squared. Okay, the r is not squared because of the r canceling the r squared out. So that's one of those things to realize, that one of the r's gets canceled out, so that's not used that way. Okay, so example 2, a ball is whirled at the end of a string in a horizontal circle of 60 centimeters in a radius at a rate of 1 revolution every 2 seconds. So find the ball's centripetal acceleration. Well, we're given 60 centimeters as the radius, which has to be converted to meters. We're also given 1 revolution every 2 seconds. So we could use that as a frequency of 1 over 2 seconds, or we could use that as a period of just 2 seconds. So you can do it either way, okay? So if I say that my R value has to equal 60 centimeters, which converted is 0.6 meters, and then I would probably use my period as 2 seconds, then I could just plug that in as my T value in this formula and solve from there, okay? So lots of different ways to look at it. I could also say it was the frequency of 1 revolution over 2 seconds. So it was 0.5 hertz. Okay. All right. So you should get 5.92 meters per second squared. It is an acceleration value, so it has the same units that we've always been dealing with for acceleration. Again, double check your calculations. Don't forget the squared on the period, and don't forget the squared on the pi. All right? All right, so let's talk a little bit about centripetal force. Centripetal force is an inward force again, remember, to maintain uniform circular motion. It is from Newton's second law, and so F equals ma, but since we're talking about centripetal force, we can substitute in the formula for centripetal acceleration, so we would have F equals mv squared over r. So either one of those works, because again, a force is a force is a force, and we're using Newton's second law, so that can work accordingly. And remember always that the acceleration and the force are vectors, so they're always in the same direction. Example 3, a 1,000-kilogram car. It rounds a turn that has a radius of 30 meters at a velocity of 9 meters per second. How much centripetal force is required for it to stay on the actual road? Okay, so we know our mass, we know our radius, and we know our velocity. So we can use our F equals ma. We can substitute v squared over r for our a. We can then say 1,000 kilograms times 9 meters per second squared divided by 30 meters can give us a force of 2,700 newtons. Well, where does that force actually come from? Okay, what you need to realize is that comes from the traction between your tires and the road. That is why there's a speed limit sign to go around curves most of the time, because this force has actually been calculated, and so since we know this force for the normal surface of the road between the tires and the road, then we can actually, and we know the radius of the turn, we can calculate the speed that you can go around the curve. So this would be just rearranging the formula and solving for this v value right there. So that's how that speed limit sign around curves is actually found, even though we all know we actually go around that a little bit faster. That's actually calculated for adverse conditions, just to let you know. So that's when the tire traction is not as good. But that's where that force actually comes from. It's a frictional force. I will tell you something that you need to understand. Centripetal force is not an actual force. It is a force that's created by a string or by friction. It's created by something else. It's not an actual force that exists. Notice I even have it on my free body diagram as a friction force. It's not a centripetal force. You don't put centripetal forces on free body diagrams. That's really, really, really important. I would make a star and put that on your notes up where we wrote information about centripetal force. It is not an actual vector on your free body diagrams. It can be labeled as a tension force or a friction force, but it will not end up being an actual labeled force as efficacy. Okay, it's created by other forces. Okay, I'm not actually going to record this. We'll watch it again later in class, but it eats up a lot of this video time with my recording, so we're going to skip past the slide. I promise I'll show it in class when I'm back. All right. If we think about a ball on a string, satellites are an example of uniform circular motion. If we have, they're called geosynchronous satellites, but actually that centripetal force is caused by universal gravitational force. So there is one speed that the satellite can have for it to maintain a fixed orbit. Actually, all of our communication satellites are like this because they need them to be in one location so that we can have our cell phones. Satellites work this way. Okay, so the gravitational pull between the Earth and the satellite is what creates the centripetal force, though, and so it acts like an invisible guideline or wire between the satellite. So we could actually look at it as F equals gm1 m2 over r squared, which we already know this formula from when we talked about forces. And then we also know that force equals mass times acceleration for centripetal force. So if we set those equations equal to each other, then we have m on both sides, so the m can cancel out. So then we can actually figure out the velocity by rearranging that equation and saying the square root of g and the mass of the object that we're orbiting, whether it be the Earth or whether it be, the moon, whatever we're trying to put the satellite around, as far as, and as well as the radius of that object. So those are some things that we would need to know. Okay. So a geosynchronous satellite is one that stays above the Earth's equator. And to determine the height above the Earth, we could also figure that out. If we know the mass of the Earth and the radius of the Earth, we know that it has to orbit one circle in one day. So that would be 86,400 seconds. We know the universal gravitational force has to equal the centripetal force, which we could set those equations equal to each other. Then we could say that we know that V is also 2 pi r over t, so we could substitute that in as well. When we do that, we have to square all of that, remember? So it looks like this. So this is it plugged in, just squaring it. Then this is canceling out the r's here. So since there's an r here and there's an r squared there, that's where we end up with this. So this is equal to this. That's where I'm at right now. Okay. We then would have to cross multiply. And when we cross multiply, we end up with an expression that looks like this. So we have our universal gravitational constant, the mass of Earth, times the period squared, equals 4 times pi squared times r cubed, because we have this r squared right here that's going to cross multiply with this r. Everybody got me so far? Okay, remember we're trying to look for the height above the Earth, so we're actually looking for this r value, and then we're going to take the radius of the Earth out of it, okay, because this is from the center of the Earth. So then we would rearrange the equation to solve for r. We would have to take the cube root of that, and after we took the cube root, then we would actually have to subtract out the 6.38 times 10 to the 6th meters. But this is taking the cube root, so these are our values substituted in, squared divided by pi squared, okay, and divided by the 4. So this should be the value if you do the math, and you take the cube root. All right, and then we'll need to actually subtract the Earth's radius out of it. So this would be how far it needs to be from, or the height above the Earth's surface that it would be 3.59 times 10 to the 7th meters. Again, you might need to pause this multiple times as we're going along so you can keep up. And if you need me to repeat it, just rewind and keep going. Now the satellite speed, we could also find that. Again, we're just going back to the original equation, and we could solve for v. Now we would use the radius from the center of the Earth, which would be our 4.23 times 10 to the 7th. So that's important to realize. That's why I scribbled out this e value right here, because that shouldn't have been there. Okay, so then we have our 4.23 times 10 to the 7th meters substituted in, along with the mass of the Earth, and our 6.67 times 10 to the negative 11th constant from our formula chart. When we take the square root of that, we come up with our 372.54, and this is meters per second. All right. So again, I went through this really, really fast. I will probably post this one on my YouTube channel as well, so you guys can go through both of them, or if you need to go back over it at any time, you can. All right. Now I'm going to stop here with the conical pendulums, and we will talk about conical pendulums in class. All right. I will see you the next day in class. All right.